Chapter 11 of the ABC of Atoms. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The ABC of Atoms by Bertrand Russell. The structure of nuclei. The facts known about the structure of nuclei are not sufficient to enable us to be very definite as to the way in which they are built up. Let us begin by setting forth the facts and then see what is to be inferred in the way of theory. The most important facts for our purpose are those of radioactivity, which we consider in the previous chapter. We know from these facts that the nuclei of certain heavy atoms contain helium nuclei and electrons, that the loss of a helium nucleus diminishes the atomic number by 2 and the atomic weight by 4, while the loss of an electron increases the atomic number by 1 and has no appreciable effect upon the atomic weight. We know also that it is possible for several different elements to exist with the same atomic number, but different atomic weights. In radioactivity, these can be seen in process of formation, but they are found to exist among lighter atoms which show no discernible trace of radioactivity. It is possible that radioactivity, in a very slight degree, exists among elements which appear to us perfectly stable. The amount of it may be so small that we cannot hope to detect it. This may be the reason for the existence of isotopes, but there is at present no positive evidence in favor of this view. Another fact of immense importance has been experimentally established by Rutherford. Some elements, but not others, when submitted to a very intense bombardment by alpha particles, give off rays which are found to be hydrogen. The element in which this result has been established with the greatest certainty is nitrogen, atomic number 17. But it is also fairly certain as regards a number of elements, broadly speaking, those which have odd atomic numbers. Rutherford is led to the conclusion that hydrogen nuclei can be detached from the nuclei of other elements, unless their atomic weight is a multiple of 4, which is the atomic weight of helium. This, together with the fact that in radioactivity, helium nuclei, but not hydrogen nuclei, are thrown off, leads irresistibly to the view that every nucleus is composed as far as it can be of helium nuclei. Thus phosphorus, which has an atomic weight of 31, may be supposed to consist of 7 helium nuclei, each having atomic weight 4, and 3 hydrogen nuclei, each having atomic weight 1. The 3 hydrogen nuclei could, with luck, be detached by bombardment, but the helium nuclei are to be regarded as incapable of being destroyed by an alpha particle, so that if they are detached as wholes. Consequently, when the atomic weight divides by 4, the nucleus can be supposed to consist wholly of helium nuclei, and there will be no odd hydrogen nuclei to be broken off. It is impossible to know whether Rutherford's bombardment breaks off helium nuclei, because they could not be distinguished from his projectiles, which are also helium nuclei. The atomic weight, which we have hitherto found less important than the atomic number, is of course of the greatest significance when we are considering the structure of the nucleus. The weight of an electron is so small as to be negligible in comparison with that of the nucleus, even in the case of hydrogen, so that the weight of the atom is, to all intents and purposes, the weight of the nucleus. If we take the weight of the helium atom to be 4, the weight of the hydrogen atom is just over 1. The explanation of the fact that it is not exactly 1 is very interesting, and we shall return to it shortly. The weight of every other atom, in view of Aston's work on isotopes, is apparently a whole number, as nearly as our measurements can determine. Roughly speaking, the atomic weight is about double the atomic number. This is true exactly in the following cases, making in some cases inferences allowed by Aston's work. Helium, atomic number 2, atomic weight 4, carbon, atomic number 6, atomic weight 12, oxygen, atomic number 8, atomic weight 16, neon, atomic number 10, atomic weight 20, sulfur, atomic number 16, atomic weight 32, calcium, atomic number 20, atomic weight 40. After this, the atomic weight is always more than double the atomic number. It will be seen that the above elements all have even atomic numbers and have atomic weights which divide by 4. We may therefore regard their nuclei as composed wholly of helium nuclei. In the case of elements which have odd atomic numbers, there is only one instance, nitrogen, in which the atomic number, 14, is just double the atomic number, 7. In this case, we may suppose that the nucleus consists of 3 helium nuclei and 2 hydrogen nuclei. In other cases, in the early part of the periodic table, the atomic weight is greater by 1 than the double of the atomic number. Thus, phosphorus has the atomic number 15 and the atomic weight 31. The same is true of the other early elements with odd atomic numbers except nitrogen. From the 21st element onward, the atomic weight is larger than it would be by this rule. The inference is that the nuclei of atoms which have odd atomic numbers usually consist of an adequate number of helium nuclei together with 3 hydrogen nuclei. The peculiarity of nitrogen is perhaps connected with the fact that Rutherford found it the easiest element from which to detach hydrogen nuclei. The fact that the atomic weights are whole numbers, together with the facts of radioactivity and of Rutherford's bombardment, lead irresistibly to the conclusion that the weight of an atom is due to helium nuclei and hydrogen nuclei which exist together in its nucleus. The overcrowding in the nucleus of a heavy atom must be somewhat fearful. Radium-C, which emits the alpha particles that Rutherford used in his experiments, has a nucleus whose radius is about 3 million millionths of a centimeter, about 1 million millionth of an inch. Its atomic number is 83 and its atomic weight is 214. This means that in this tiny space it must contain 58 helium nuclei and 2 hydrogen nuclei. It must also, as we shall see in a moment, contain 131 electrons. It is no wonder that helium nuclei and electrons move fast when radioactivity liberates them from this slum. The beta rays show that the nucleus of an atom contains electrons. This appears also from the fact that the atomic number, which represents the net charge of the nucleus, is less than the atomic weight, which represents the gross positive charge. Each hydrogen nucleus contributes 1 unit of positive charge. The difference between the atomic weight and the atomic number represents the number of electrons there must be in the nucleus in order to bring its net charge down to the atomic number. In this argument, however, we have assumed that the helium nucleus itself consists of 4 hydrogen nuclei and 2 electrons. We have still to examine the reasons in favor of this view. There is no experimental evidence that a helium nucleus can be broken up into hydrogen nuclei and electrons. Radioactivity and Rutherford's bombardments show that the helium nucleus is very stable, and that no known process will disintegrate it. Nevertheless, it is believed by all students of the subject that the helium nucleus consists of 4 hydrogen nuclei and 2 electrons. There is first of all the argument from the atomic weight. The weight of the helium atom is so nearly 4 times the weight of the hydrogen atom that we cannot bring ourselves to attribute this fact to chance. But why is it not exactly 4 times the weight of a hydrogen atom? If we take the weight of a helium atom as 4, that of a hydrogen atom is not 1, but 1.008. According to everyday notions, this would be impossible if a helium nucleus consisted of 4 hydrogen nuclei. The electrons may be ignored, as their contribution to the weight is negligible. We are used to thinking that if we place 4-pound weights in a scale, they will weigh 4 pounds. This, however, is only approximately true. In ordinary cases, it is so nearly true that we could never discover the error experimentally. But in extraordinary cases, such as the helium nucleus, it may be sufficiently untrue for our measurements to be able to detect the difference. It used to be thought that the mass of a body, which is the scientific conception that replaces the popular conception of weight, could be defined as the quantity of matter. But Einstein has revolutionized the conception of mass, as well as all the other elementary conceptions of physics. Mass is now absorbed into energy, and the mass of a body is not by any means always constant. This subject of the variability of mass will be resumed in Chapter 13. A system of electrons and hydrogen nuclei may have different amounts of energy in different arrangements. When the system passes from an arrangement with more energy to one with less, the energy it loses is radiated into the surrounding medium, in the sort of way with which we became familiar when we were considering the spectrum of hydrogen. When the system loses energy, it also loses mass. The loss of mass is very small compared to the loss of energy. It is obtained by dividing the loss of energy by half the square of the velocity of light, which is enormous. When the system has arranged itself in a shape in which its energy is diminished, it can only go back to its former shape if the lost energy is supplied from outside. Therefore, the shapes involving least intrinsic energy are the most stable. This is what we must suppose to happen when 4 hydrogen nuclei and 2 electrons come together to make a helium nucleus. They arrange themselves in a configuration in which their energy is less than when they were separated. The loss of energy can be inferred from the loss of mass or weight, to speak popularly, and is got by multiplying this loss of mass by half the square of the velocity of light. This represents an enormous amount of energy. Sommerfeld calculated that it is about 10 million times greater than the amounts involved in chemical combinations, for instance in combustion. The helium nucleus could only be disintegrated by supplying this amount of energy from outside, which does not happen in any known natural process. Thus the loss of weight in the helium atom is accounted for, and by the same argument the extreme stability of the helium nucleus is explained. It is clear that, for the sake of unity and simplicity, it is desirable, if possible, to regard the helium nucleus as consisting of hydrogen nuclei and electrons. If we do not do so, we shall have to admit the helium nucleus as a third ultimate constituent of matter, having by a strange coincidence just twice the electric charge and 4 times the amount of matter that exists in the hydrogen nucleus. It must be admitted that this is a possible hypothesis. There are no known facts that prove it to be false. But until we are forced to adopt it, we shall prefer the simpler view that the helium nucleus is complex, like every other except hydrogen, and that its relations of mass and charge to the hydrogen atom are not a lucky fluke. Everything known about nuclei is consistent with the hypothesis that they are composed of hydrogen nuclei and electrons. The evidence that they consist of hydrogen nuclei, electrons, and helium nuclei is overwhelming. The further step which dissolves the helium nucleus is more or less hypothetical, but it is a step which we may take with a reasonable assurance that it will prove justified. The study of nuclei is still in its infancy, but is likely to make rapid advances in the near future. Meanwhile, we may assume, though not with complete certainty, that all matter consists of hydrogen nuclei and electrons, which are therefore the only elements in the strict sense of the word. Whether these two will ultimately prove to be modifications of one more fundamental substance, it is quite impossible to say. For the present, they represent the frontier of scientific knowledge, and what lies beyond is as yet mere speculation. As to the way in which the 4 hydrogen nuclei and the 2 electrons are arranged in the helium atom, mathematical considerations ought to be able to give us information, but so far they have not given much. One model which is suggestive is the following. Imagine a somewhat primitive wheel with 4 spokes, and an axle that sticks out some distance to either side. Place the 2 electrons at the ends of the axle, and the 4 hydrogen nuclei at the ends of the spokes, and imagine the wheel going round with suitable velocity. The wheel and spokes and axle are of course imaginary, and are only intended to illustrate the relative positions of the nuclei and electrons. This gives a configuration which has a certain degree of stability, and a faddish shape which is indicated by a certain amount of experimental evidence. It seems, however, that the degree of stability in this model is less than that required to account for the fact that no known process will disintegrate a helium nucleus. There is also a difficulty as regards the size of the helium nucleus. Taking our model and applying the quantum theory to the revolutions of the hydrogen nuclei, we can determine the radius of the circle in which they move, as we determined the minimum orbit in the hydrogen atom. The result is that the size of the radius should be about 5 million millionths of a centimeter. This is about 17 times too large, according to Rutherford's experimental evidence. It is possible, nevertheless, that our model may be right, because the forces between electrons and hydrogen nuclei may obey different laws at such very tiny distances from those which they obey at ordinary distances. We may hope to know more on this subject at no distant date. but for the present we must remain in doubt. End of chapter 11.